My name's John Starck.
I'm Joris.
Hi, I'm Brice.
So I'm Philippe Bekaert.
My name is Knop.
Hello, I'm Jonas.
My name is Philipp Slusallek.
Hi, I'm Purvis.
Hello, I'm Farshad Einabadi.
My name is Stefan Seibert.
My name is Knop. I'm the managing director of Stargate here in Germany. Stargate is a worldwide visual effects company, and we're very much interested in virtual production, and we use that already for years. Within Dreamspace, we are the user end partner and help the researcher partners in this project actually to evaluate and test using real-world production scenarios to make those technologies really user-friendly and also relevant to the market, to the problems that we have in our business and industry.
So I'm Philippe Bekaert from iMinds. In the context of the Dreamspace project, we work on 360 video capture technology. Here on the demo we have brought a 360 video camera that we built a couple of years ago for television purposes. One of the big problems with the live stitching algorithms is that they always suffer from seams in the image. So we came up with a solution building a camera which actually has two sets of lenses, each of them capturing a full 360 x 180 image. And that would allow us to choose where we have the seams. That's what you see here. So in the Dreamspace project, we push that further. Instead of using only one of the two sets of lenses, we use the two sets of lenses together. The two sets of lenses, they are the 360 by 180 degrees equivalent of a left-right stereo pair of cameras. A left-right stereo pair of cameras allows you to measure depth. So in the computer vision community, there are literally hundreds of algorithms that allow you to compute depth from a left-right stereo pair of camera. So how do these things work? Every scan line, every point on the scan line of your left camera returns on the same scan line of your right camera when they are properly aligned. Only the points are displaced. So objects far away appear at the same spot in both images. Objects nearby, they are displaced. And the amount of displacement corresponds with the depth, with the distance to the object. And that amount of displacement, we call that parallax. So also in the context of stitching, we call these artifacts parallax artifacts. So what have we done in the Dreamspace project? We have been applying algorithms from computer vision community to reconstruct depth, not from a left-right stereo pair of cameras, but from a 360 camera like this. So here you see what some of the very best performing real-time algorithms for depth from stereo give us in the context of these very uncontrolled circumstances we have here at FMX in Stuttgart. You see the camera really is reconstructing depth. I can walk around. You see that indeed the camera is detecting the distance to me. So what comes out is not totally rubbish, I would say, but it's definitely a nice, clean depth image. And this is the very best real-time performing algorithm that we could find. So in the Dreamspace project, we are now concentrating on filtering these depth images using recently proposed high dimensional, edge-preserving spatio-temporal filtering combined with novel global optimization algorithms. That's the kind of stuff that we do. And if you come back next year, you will see that we will have nice depth images. So what do we want to do with these nice depth images we will get next year? First of all, they will allow us to do a perfect stitching from a 360 camera. So objects nearby or far away will be stitched at the right distance, creating a nice seamless image. The second thing is, once we have these depths, we can also compute stereoscopic 360 images. But most importantly for the Dreamspace project is that we will apply this as a novel capture method for capturing backlots for virtual studio applications, which are actually on the other side of the booth here. So the whole point of virtual studio applications, virtual studio, is that you want to replace this green screen background with an image of some a real environment, an image we call a backlot. The current practice today is that you need to shoot the backlot from exactly the same perspective as you are going to use it in the virtual studio. A 360 video allows you to rotate your view around the position of the camera already. In the virtual studio, it will allow you to rotate the camera in the virtual studio. Given the depth, we will obtain an approximation of the shape of the environment that has been captured. And that will help us to also move the camera in the virtual studio. So we are developing a novel capture technology based on 360 video, including depth, that will allow freedom of camera movement in virtual studio applications. That is what we are after. So here you see some immersive movies that were made by people in our network. Immersive movies made by 360 cameras we built and using our stitching software. So the developments of Dreamspace go beyond virtual studio. They will also help to create novel virtual reality applications.
Hello, I'm Farshad Einabadi from Intel Visual Computing Institute. In the context of Dreamspace project, we have tasks around the lighting estimation and also the editing tools for the lighting matters. In this project, we propose new methods for estimation of on-set lighting, so that we can use it later for augmenting virtual assets on set with the correct lighting in different positions of the studio. So this is from the lighting capture point of view. The other point of view that we are working on it right now is the editing tools, usage of editing tools on set for the creative professionals to change the lighting on the tablet and see the details immediately. I go back to the our first contribution. So right now the state of the art is to use HDR light probes, which is valid for the approximate position which they are taken from. You can augment your assets props virtually with image-based lighting, but the limiting point with that approach is that they are valid for that certain position, and if you move your virtual assets, the lighting is not working perfectly anymore. So our proposed approach, our proposed methods in this project is to take these light probes from a couple of different positions in the studio environment, and then we developed algorithms to use these probe images as input to estimate the exact physical properties of spot sources on set. Further, we can use this estimation of the light sources individually in the renderer to render the mixed reality scenes with correct lighting. So this idea gives the creative professionals DOP, for example, to have a better correct understanding previews of what he's going to see in the post-production on set, so that he can decide better. So this is one aspect of our work. Once you have these estimations, the other way around, the Philippe side, is to use these editing clients to change the properties of the estimated light sources virtually, and then we propagate it to the real light sources. We have a small demo here. We have a DMX controlled LED light source, low power, in this small demo, and the scene is a small fish. So these editing tools that are created by our partners in Filmakademie gives the creative professional to virtually change the lighting properties, like the color, for example, and this is in real time propagated to the DMX control lights, and also we have a high performance ray traced version of the scene here, mixed reality scene, that they can decide if this is the lighting setting they want or not. They want to change the position, change the intensity, or change the color of, or other DMX controlled properties of the light sources, like the spot angle, whatsoever. So these are two aspects in the Dreamspace project we have covered so far. We have integrated the editing clients they have developed in Filmakademie, and we are aiming for real-time or interactive high performance ray trace also in this project, and we have this integration with also the real DMX light sources. This is from the integration point of view, and also from the scientific point of view, we are trying to develop our light models from spotlight sources to area light sources, as well as using light probe videos instead of light probe stills. And this is like the future directions in the rest half of this project in terms of the lighting context.
My name is John Starck and I'm Head of Research at the Foundry. And the Foundry is interested in several things inside the Dreamspace project, one of which is how to get compositing working live on set as part of production. So we have a tool called Nuke, which is a very complex, flexible pipeline tool for compositing in post-production. It allows many artists to work on a composite, and you can pipeline that through your back-end system. And inside Nuke, we have a technology called Blink, which allows you to accelerate on the GPU your compositing operations. And in the Dreamspace project, what we're looking at is how to break out our Blink pipelines from Nuke and run them live on set as part of production. And one of the interesting research areas there is how can you take your compositing pipeline, it's accelerated on the GPU, but maybe you have a machine and you can scale that up to use multiple GPUs, you want to be able to use the CPU as well, and you want to get the maximum performance to be able to get your composite to run real time.
Hi, I'm Purvis from the Foundry and the HPC team. We have produced this piece of software called Blink Player, as John said, to run Nuke graphs outside of Nuke at higher frame rates, ideally real-time frame rates. So here we have got a Nuke graph. I can show it to you, with 3 inputs and some nodes which are running on the CPU. We're achieving 6, 7, 8 frames a second here, and you can see a simulation of the passing of time, the CPU colored red as it computes the operations in the graph. Now Blink can not only run on the CPU but also on GPUs with CUDA and OpenCL with numerically identical results, so I can get exactly the same result running on the GPU here. In this case the GPU is significantly faster, we're now getting 37 frames a second. There is a second GPU in this system which I can also run on. It's a slightly slower GPU, so it only achieves 27 frames a second. Now, with numerical identity of results between the different devices, it's also possible to partition work between the devices to try and reap a greater benefit, a greater frame rate. So we can do that here. I can create an even partition of the graph between all of the devices, but you'll notice that the frame rate has now collapsed down to 11, 12 frames a second. This is barely faster than the CPU and significantly slower than the GPUs in the system. So we can see that while it's possible to get a correct image partitioning over the devices, naively the frame rate is not particularly interesting. We have, however, developed an algorithm which allows for intelligent partitioning of graphs over devices to try and reap the maximum possible benefit, and we can do that here, where we now achieve about 47 frames a second. This is significantly faster than was possible with any of the individual devices. So to visualize what's happened, you can see here now that we are working with all 3 devices. We've got red, green and blue present in this, but we have made far fewer partitions, and it's through this mechanism that we can achieve the highest possible frame rates on your system.
So one of the areas we're working on in Dreamspace is live depth capture on set. You can imagine that in a number of years' time we might be able to capture RGB-Z on set to be delivered to post for compositing. So we're interested in the type of tools that you might need in post-production that can deal with depth data. And one of the bottlenecks in post-production is rotoscoping, separating out the different elements in the shots so that you can work with it and composite on different layers. And that takes a lot of effort. And we want to see if it's possible to automate that process using the depth that you've got from a shot. So you can imagine here you're shooting and you can pull out the depth of this actor in your shot that separates him from the background. Now without that depth data, it actually is quite a laborious process for an artist to pull what would be called an image-based key. They would have to procedurally set up a key that separates out the artist into a single layer by working around the shot and setting the background color that separates the background from the foreground. But if we can add depth data into that, we can start to automate that process to pull a key all around the entire border. And that shows the result that we get from a preliminary set of tools to automate that matting process.
Yeah, my name is Philippe Slusallek. I'm a director of research at the Intervisual Computing Institute and the German National Research Center for Artificial Intelligence. And our job here in the Dreamspace project is to accelerate realistic rendering and realistic lighting computation through, in particular, a new compiler technology that we've developed called NEDSL, which allows us to describe algorithms such as ray tracing, which is used for rendering these kind of very realistic images, at a very high level in just like textbook style code. So it's very easy to describe the algorithm, but at the same time we enable the developer to describe how to map the algorithm to a different hardware. And then we can optimize this code in a way that was not be possible before. And so we can get, with very little development effort, highly realistic rendering code that runs with optimal performance on very different hardware architectures, from GPUs to CPUs and others as well. At this point in Dreamspace, we've worked mostly on the compiler technology itself, and we have some initial ray tracing code here. And this has been integrated into the Katana renderer by the Foundry. And what you see here on the screen is just two different renderers, the ray tracing renderer as well as a rasterization-based renderer. And so I can, by grabbing the slider here, I can actually just switch between the two. And for instance, here you see that here on the left, the shadow is being integrated through the rendering. You also see here at the floor the shadows cast by structures at the top. And so it's very easy to kind of integrate high-performance, realistic rendering for virtual productions through this new compiler technology that we're developing. So in this case, we're showing two renderers, a ray tracing-based renderer and a rasterization-based renderer is on GPUs. And we can show the difference between the two by just sliding here between these versions. And so in particular here on the left-hand side, you see that with the ray tracer, we can include the shadow computation. Right. You also see that here the structure of the floor, which is actually shadows cast by other structures in the ceiling. And so the interesting part is that we now have a highly scalable and pretty fast ray tracer, and the compiler allows us to program that in very easy ways.
Hello, I'm Jonas from the Filmakademie, and I'm currently working for the Dreamspace project, and we are developing on-set editing tools for the virtual content. So when you are standing in a studio, you should be enabled to edit the virtual content in the scene just with this tablet or other devices. So we can select the objects that you want to modify. You can translate, rotate, scale them. Just by pointing at them and pushing them where they should be. And we also were developing tools to do this more interactive, more intuitive. We have different modes where we can actually attach the object to the camera and tilt the camera, and thereby replace the objects, and thereby, yeah. Or we can just point to the ground where the object should move and move those objects there. We could also not have the view of the actual tablet tilting around, but we can also synchronize with the ncam view, so the tracked camera view, and see the virtual scene as if it was filmed by the real camera. On set we want to enable everybody to interact with the virtual content, so each person on set should be able to edit the set without any knowledge in 3D content creation or something. So on set we can have multiple tablets, and if we edit something on one tablet, it will be synchronized to all the other tablets as well as to the live view system. So the live view system is actually a more production-ready rendering of the scene, and all the editings I'm doing here are synchronized to this and will be rendered in real time.
My name is Stefan Seibert. I work at the Filmakademie for the Dreamspace research project. And what we have here is the Meta space glasses. The basic idea of this device is to fulfill augmented reality. So you are not only see the virtual object, you can also see the real world. So this is not a closed device. You can look through it and see the real environment. And so you are enabled to render virtual object into the real world. So if you imagine a virtual or a film set where you have real actors, you have real props, and you can add to these real scenery virtual objects and combine these with these glasses.
Hi, I'm Brice from ncam, and I will talk to you and present to you what we've done inside the Dreamspace project. Then let's start by a few words about the ncam company. Then ncam is usually a company creating solutions for having real-time tracking on set of the camera. Then it is a system that doesn't rely on artificial markers. Then there is nothing to put on the ceiling, nothing on the ground, and there is no survey of the environment to do before being able to use the system. Then this is a system that is tracking through a camera bar. That is something we designed for it. Then it uses two witness cameras that are fisheye lenses, and also different sensors that are integrated in the bar. Then ncam is a sensor fusion algorithm that will take the best of each information for being able to provide that track in real time on set on most of the situations. Because we are using that kind of camera, we can go on every different setup for the cameras, and that can be handheld, pedestal, crane, and whatever buggy, helicopter. Then in this project, we've been interested to try to extend what we can do on set. Today, there's usually two use cases. Then using a green screen like the one I have behind me, or without a green screen. When you have a green screen, the CG in real time will be integrated always behind me, and that's something that can be disturbing if the CG piece should be in front of me, like a window or a tree or a piece of the environment. On the other side, if we have no green screens, then the CG will always overlay me. And this is something that is disturbing for the operators. And if we want to save time on set, we have to provide a way to handle the dynamic occlusions on set. And this is something we've been working on for that project. This is still a work in progress, but I have a few first results I can show you. Then you can see in this screen a real-time integration that is a regular keying algorithm. But if, let's say there's a window, okay? I'm going back and I should go through the window. With the technology that has been developed in that project, we are now able to handle that kind of environment. This is also an information that is really useful when you want to provide, I would say, a really nice estimation of the ages of the actors, because that's something you need, for example, for the final compositing. As we're speaking about the final compositing, you can see that the rendering we have now is not perfect. Then this is why in this project we're also having an interesting work that has been done on extracting the lighting conditions in real time. There's also some other work that has been done to estimate 360-degree videos. Then this is, for example, that kind of videos that can be used to be projected behind me. And here is an example of the regular keying that happened on green screen. Then we can see that the CG has been placed on behind me, but the problem is usually if you don't have the depth sensing, you'll not be able to have that kind of composition. Then this one works because I'm behind the CG window. The regular ways of doing it will say that the window is always behind me, disturbing the operator. Then the depth information is also really something interesting for the whole VFX pipeline. For example, the Foundry have been working on the new ways to extract the mate of the real characters for doing, I would say, the final composition. There's also some interesting work that has been done about acquiring the lighting environment of the set for being able to relight the CG according this information and really trying to say, okay, what you see on set is what you'll get at the end, and trying to reduce all the steps to reduce time and just give a better, I would say, reducing time on boring thing to increase time on a creativity side.
Okay, so inside the Dreamspace project, the Foundry is working as the integration partner. We've got a lot of technologies that we're working on that span through the production pipeline. And one of the interesting questions we have is how can you unify the pipelines that you have throughout pre-production, production and post-production? At the moment there is a divide between the different pipelines that are used. So in post-production, the Foundry has a toolset called Nuke for compositing and Katana for setting up geometry, lights and materials and interfacing those with renderers. So these are very complex technical tools that are used as back-end pipelines. And what we're looking at inside the Dreamspace project is it possible to use these pipeline setup tools to set up what you would use on set at the time of shooting? So what we have here is a prototype tool called Katana Player. And what we've done is we've set up the geometry pipeline to interface renderers inside Katana. We've broken that out to work headless so that it can run using a real-time renderer such as OpenGL live on set, and also switch to a final quality render, be it Arnold, V-Ray or PRMan, so that you can get final quality snapshots of final quality rendering at the time of shooting. And also within the research project, we've partnered with the University of Saarland, who are working on frameworks to create scalable renderers that can make the maximum use of the hardware available to be able to accelerate the performance of ray tracing. So we've got a first prototype here that's comparing an accelerated ray trace renderer from the University of Saarland against PRMan. So we can run both of those to give a snapshot of the final render on set. So inside this prototype tool, we have Katana feeding our different renderers. On the left-hand side, we have the high-performance ray tracer that's being developed at the University of Saarland, and on the right-hand side, we're feeding PRMan 19. And we can just take a look at the difference between these two renderers now. And if I move the camera around, it'll take a few seconds to resolve, and then you'll see the difference that you can get between the two renderers. So our high-performance renderer has now completed, and we're going to see PRMan resolving on the right-hand side.
I'm Joris, I'm part of Crew. Crew is a partner inside of the Dreamspace project. So we're a user partner, so we are developing technology which we immediately try to put into use to see what we can do with it. So the whole project is about virtual production technology. We're not into cinema, so we're trying to see how can we use this powerful, potentially interesting parts into something else. So we are working into a scale which goes more to the individual. In fact, nearly all the kind of things we do are kind of experiences which are anchored into the body. So these are personalized experience in immersive experiences. So Crew is an arts company. In fact, we are working inside of the theater, but since 15 years, we developed technology to use upon the stage and also to bring the stage somewhere else, mainly inside of the body. So we are an experimental type of theater. We tour around Europe, around the world, and we make performances with the immersive technology which is being developed. So that means that all spectators are protagonists, are immersants, as we call them. And generally, you can see that the whole market is also going to more individual use of technology, even in terms of cinema. So many people are watching movies on the PC now, so that gives additional possibilities for treating that differently. So to go back to Dreamspace, the fact that Dreamspace is making a collaborative environment with collaborative tools, that opens up a lot of things for use, for other users. The fact that there is a lot of work which can be turned into viewer-dependent type of displays is also very interesting. It's interesting for the immersive worlds, since the constraints we have to do with the fact that you can look around freely inside of an image. You can walk around, as we do all the time, physically walking around, but you have to consider the path which has been followed by the camera. So we want to go to free, unconstrained spaces, so where you can freely walk inside of environments. And the most important part inside of the Dreamspace project for us is, can we also get rid of the headsets? So the idea is to have projected environments. We call them holographic, in the sense that as you walk along the image which is displaying objects or anything will show the different sides, so which will give you a true feeling of space. So as I move in space, this is moving faster than that. That's why I know that this is closer to me, which is a different solution from stereographic type of use. So to build environments, filmed environments, we're not talking about computer graphics, but to have captured environments, combining 360 degrees of iMinds with depth view and projecting that in kind of 3D viewpoint mapping. That's the kind of worlds we want to create.